All right, so good morning. What we will do is discuss this problem from the chapter of wave optics. This is a good problem on the YDSE setup, right? Interference of waves. So let's discuss this problem. Before I start doing this question with you, let's discuss the key concepts. Okay, quickly. I will not take too much time, very little time, but we will revise the concepts. First concept you should know is the fringe formation and path difference, right? And I will relate these concepts to this problem. So the path difference is when it is multiple of lambda, it is a constructive interference. When it is n plus 1 by 2 into lambda, which means lambda by 2, 3 lambda by 2, the path difference is for a destructive interference. So a dark fringe is obtained. Now let's talk about the fringe width. In this question also we have fringe width. So lambda d by d and fringe width remains constant throughout the pattern because the lambda capital D, the distance of the slits from the screen and the separation of the slit is given in an experiment and is fixed. So therefore the fringe width everywhere you get is same. Okay? Very important concept which you will use here. What is the effect of wavelength? How does wavelength, if you change the wavelength, what happens to the experiment? If you, for example, use a higher wavelength, then the wider fringe pattern is obtained. If you use a blue color for the purpose of experiment, which is blue wavelength, then the experiment will show you a narrower fringe pattern, right? It will not expand as much. The fringe, as you can see, is also dependent on wavelength. The smaller wavelength means narrower fringe width and the pattern becomes smaller. Okay. Now let's talk about the phase difference. The phase difference is calculated using the path difference in the YDSE, right? So you know the conversion. 2 pi by lambda into delta x will give you the delta, which is the phase difference. What is the intensity? Intensity is given by 4I naught cos square delta by 2. You can see the expression for the maxima, and for the minima it is 0. What is the role of slit width? Very important concept. The slit width is key. Okay, the slit width and the slit separation are very important. The slit width has to be kept very small so that the experiment is prominently displayed because the diffraction is good in a narrower slit width. The slit separation also is very, very important and generally has to be kept very small as compared to the distance, the perpendicular distance of the screen from the slits. Small d should be very small as compared to the large d. If you don't do that, you will have to find the path difference in another manner. Because when d is very small as compared to the capital D, the small angle approximation can be applied, which I've written in the last. Okay, so the fact that if you do the calculation of S2P minus S1P, the path difference which the waves travel from the first slit and the second slit, comes out to be, if you remember, YD by D, right? That path difference has to be achieved or calculated using a small angle approximation, which is possible when small d is very small as compared to capital D. So much for your quick revision of YDSE. So the assumption is you know most of the stuff. I'm quickly revising and let's go to the question now. In this question, what you're given is a YDSE setup is available to you with the wavelength of the setup is 6000 angstrom and the fringe width is beta. Okay, the fringe width available to you is beta. What are you supposed to do? You're supposed to calculate the fringe width when the whole experiment is immersed in a water or some material of refractive index 1.33. It's a liquid. Now let's see what happens and listen to this video till the end because I'm going to tell you a key concept in the end, which is not part of the question. So listen through. So once you immerse the whole experiment in a liquid of refractive index 1.33, right? Let's see what is the concept you have to use. The question is, what is the fringe width? New fringe width in liquid. So this concept, the fringe width, and this concept, both the concepts get utilized. We studied what is the impact of wavelength, what is the impact of fringe width and spacing, right? What is the impact of lambda d and d, sorry, on the fringe width? Now, if you see the refractive index, right? Refractive index, what does it mean? The wave travels slower, right? So the way we write this is lambda A upon lambda medium, right? This is the way we write refractive index of the medium with respect to air. Okay, so lambda air is given to be 6,000. This is available as 1.33. I'm going to write it as 4 by 3 actually. So this is lambda medium, and lambda medium is given by 6,000 into 3 by 4, and this is 1500 is equal to 4500 angstrom. So you can see the wavelength has gone down. I told you if the wavelength, the d and the small d are kept just like that, the fringe width will remain same throughout the experiment. But here what we have done is we have changed the refractive index. Indirectly, what we are saying is we have changed the wavelength. So if the wavelength undergoes a change, right, which is you have to find beta in, sorry, the wavelength in the new liquid is 4,500. Let's use this formula, right? So beta 1 is equal to lambda 1 d by d. We have not changed d and d here, right? So beta 2 is equal to lambda d by d. You divide beta 2 by beta 1 is equal to how much? It is equal to lambda 2 by lambda 1. So you can see that beta 2 will be equal to 2 into 4,500 divided by 6,000. So this becomes 3s are 4, 2, and this becomes 1.5 mn, right? So we have been able to calculate the new fringe width in the experiment. Okay. However, the mystery is yet to be solved. Let's discuss in the context of the path difference and phase difference. So you have been able to get the new fringe width, but what happens to the path difference and what happens to the phase difference? So if you know the path difference, right? If you are inserting the whole experiment in a liquid, right? So this is your liquid in which the whole experiment is immersed, right? And my question is, what happens to the path difference? What happens to the phase difference in this situation? Well, let's think through about the path difference, right? The formula of path difference, and I will make it mathematical actually. So the path difference is actually given by x d by d, right? So it is put equal to n lambda for maxima and stuff like that. As you can see, what is happening is your lambda has gone down. Your wavelength has gone down, right? So to maintain the same path difference, you will need more number of waves. To maintain the same path difference, you will need more waves, right? So effectively what happens is, since you need more waves, your effective path difference in the liquid has gone up. How do we prove that? We know that the value of, when we convert the path difference, right? A path difference of lambda results in 2 pi phase difference, right? So I'm now talking about phase. So one path difference is 2 pi by lambda. And if you have delta x, right? So this becomes delta x. So your lambda has gone down, right? Your lambda has gone down. So your phase difference has gone up. So which means more number of waves have to be accommodated. Effective path difference has gone up because path difference is a multiple of lambda. Effectively, the decrease in wavelength, right? If you see this, the wavelength has gone down. What is the impact? The impact is that the path difference, because the lambda has gone down, the path difference has increased, right? And therefore, for the same value of x d, if lambda has gone down, the value of n goes up, which means the at the same position you will have more waves arriving. Okay, so this is a very important concept. Path difference change happens when you immerse the liquid, and so does the phase, right? This is the way you need to look at this problem, not just purely a problem which has refractive index, but also think in terms of a decrease in lambda is increasing the path difference, right? And to keep n lambda as is, we increase the value of n, which means more waves are accommodated. So I hope this made sense to you and you enjoyed this video. Think through this concept. These are the basic concepts, but a lot of questions that you get are indirect in nature. So thank you very much and wait for my next video.